Hello, and welcome to our video covering the topics in section 6.2 that we didn't get to in our last video. In particular, we're going to discuss some more properties of the determinant and then discuss the determinant of a linear transformation. All right, the determinant of a product. Let's start here. You will be pleased to know that actually the determinant, if you have two n by n matrices, A and B, you'll be pleased to know the determinant of the product is the product of the determinants. That's always nice. All right, let's see why this is true. First, let's handle the case where A is not invertible. The claim is, well, if A is not invertible, then neither is neither is AB, and so both are going to have determinant 0, and both the left and right hand side here will have determinant 0. So why is this true? I think your book says something like, think about the image, but I'll go into a little more detail. So first, assume B itself is also not invertible. Then, if you have some non-zero vector in the kernel of B, that's also going to be a non-zero vector in the kernel of AB, and so AB won't be invertible. If B is invertible, then its image is all of Rn, and so some vector in the image is going to be in the kernel of A. So yeah, there exists a non-zero vector x such that Bx will be non-zero and in the kernel of A. And so this vector x is going to be in the kernel of AB. And so once again, you have that if A is not invertible, neither is AB. So there we go. We get that the determinant of A times determinant of B is going to be 0 times the determinant of B, which is 0. But then also, because AB is also not invertible, this determinant is 0. And we get this equality. All right, so what about in the case where A is invertible? Well, in this case, we have this handy theorem that says that the reduced row echelon form of the matrix you have where you take A and then augment it by the matrix AB, that the reduced row echelon form of this is equal to the identity matrix augmented by B. So it's sort of like if you are doing reduced row echelon form, you're kind of transforming both the A on the left and the right into the identity. And so why is this true? Where have we seen this before? How do you prove this? You prove it by doing your homework. So yeah, this is going to be a homework problem, and I think the book guides you through how to prove this. But okay, we're going to take this property for granted. But what does it mean? It means that the row operations required to get from A to the identity, these are the same row operations that are required to get from AB to B. So, all right, let's suppose that in order to get from A to the identity, we have to swap rows s times, we divide various rows by these scalars, and maybe we'll also add some multiples of rows to another, but as we've already seen, that doesn't affect the determinant, so we're going to kind of ignore that. But okay, if you have s row swaps and you divide rows by scalars k1 to kr to get from A to the identity, then as we saw in our previous video, this means that the determinant of A is equal to minus 1 times the number of row swaps times the scalars that you divided out times the determinant of the identity matrix, or in the what we saw last video, this would be the determinant of the reduced row echelon form, but in this case, reduced row echelon form is the identity. So really, this is telling us that if A is invertible, then the determinant of A is just minus 1 row times raised to the number of row swaps times these scalars. So okay, now let's think about what's the determinant of AB. Well, since the row swaps and dividing by scalars are the same in going from A to the identity as from going from AB to B, then we have that the determinant of AB is just minus 1 times raised to the row swaps times these scalars times the determinant of B. And then we notice, this right here, that's the determinant of A. And so there we have it. We get that even when A is invertible, the determinant of AB equals the determinant of A times the determinant of B. Cool, this is nice. In fact, there are two nice consequences that come pretty like right away from the product property. So the first is a relationship between the determinants of similar matrices. And so the claim is if A and B are similar, then their determinants are the same. Let's see why that's true. Okay, well, if A and B are similar, then there exists an invertible matrix S such that AS equals SB. This is just definition of similar matrices. So, all right, the determinant of AS must equal the determinant of SB. Now let's use our product property. Determinant of A times determinant of S is determinant of S times determinant of B. And then since S is invertible, the determinant's non-zero, so we can cancel that and just get that the determinant of A is the determinant of B. Cool. Here's another nice property. If you know the determinant of A, can you calculate the determinant of the inverse easily? Yeah, if A is invertible, then the determinant of the inverse is just 1 over the determinant of A. So we can see this by saying like, all right, well, 1, that's the determinant of the identity, but the identity is just A times A inverse since A is invertible. Product property says that 1's equal then to the determinant of A times the determinant of A inverse, and then you just divide through by the determinant of A. There you go. All right, something a little bit more involved. Let's talk about the determinant of the transpose. Once again, you'll be relieved to know that the determinant of the transpose of A, if A is square, it's just the same as the determinant of A. So that's really nice. And we've seen the transpose come up a lot, so nice to know that we've got this. We've got this property. All right, so how do we prove it? Well, first, again, let's start with the case, suppose A is not invertible. Well, then neither is A transpose, and this is from theorem 5.3.9, which says that the rank of A is equal to the rank of A transpose. So if A doesn't have full rank, neither does A transpose. And so both of their determinants are 0. And so, sure, their determinants are equal in that case. Okay. What about when A is invertible? How do we handle that case? How do we show that the determinant of the transpose is still the determinant of A? Actually, let's hold on to that thought. We'll return in a moment. There's something else I want to talk about before we prove this. So here I want to discuss the matrices of elementary row operations. So the row operations that you do when you do Gauss-Jordan elimination actually can be performed via matrix multiplication. And so let's talk about what those matrices look like. This is a topic that is discussed in your textbook in the exercises way back in section 2.4. But it's good cultural knowledge, and it's finally relevant, so I'm shoving it in here. Okay, so let's think about swapping rows I and J. What matrix could you multiply by the matrix A to swap the rows? I claim it's this matrix here that I copied and pasted from Wikipedia. So, but I think it's right. I mean, I checked. So yeah, this matrix here is the matrix that you get when you take the identity matrix and you swap rows I and J in the identity matrix. So identity, if this was I, then this row, this is row I, gets swapped down to row J. So the one that was in II is now in JI, and the 0 that was in JJ is now in IJ. Okay. And this, if you multiplied it on the left, and if you multiplied matrix A on the left by this matrix, this will swap rows I and J in matrix A. And if you don't believe this, I suggest pausing and thinking about it until you convince yourself, or until you come up with a question and then you have something to ask in class. Okay. Now let's also make sure you convince yourselves that this is actually a symmetric matrix. So, okay, this is I don't know if I said this, but like all of this white space, that's all zeros. We've got the diagonal ones everywhere except for these zeros here. So we don't have to worry about the diagonal when we're worrying about symmetry. But remember, this took when we were swapping rows, the one that was here in II went to JI. The one that was here, JJ, went to IJ. And so the only non-zero term here is in JI, and the only non-zero term here is in IJ, and they're both ones. So when you swap everything across the diagonal, these ones are going to go to each other. Entry IJ goes to entry JI. Okay, so this is a symmetric matrix. For the row swapping is a symmetric matrix, and that means that the determinant of a row swap is equal to the determinant of the transpose of a row swap. And that's because it's equal to its transpose. So this is not anything crazy. This is just saying, all right, the matrix and its transpose are the same, so their determinants are the same. But this is, you might be able to see why this becomes handy if we're trying to prove something about the determinant of transposes in general. So, okay, now let's see what happens when you want to scale some row. So this matrix here will, if there's an M in the ith entry, so this is like the identity matrix, there's zeros everywhere else, but now there's an M in entry II. No. Again, convince yourself that multiplying matrix A on the left by this matrix will indeed scale row I in matrix A by M. And this is, again, a symmetric matrix. I mean, now it's diagonal, so it's obviously symmetric. And so once again, scaling rows means that the determinant of your matrix is going to be, the determinant of the row scale matrix is equal to the determinant of its transpose. Finally, what if we're going to add some M times row J to row I? So adding a multiple of one row to another. Well, this is the matrix that does it, where, again, this is like the identity matrix, one's on the diagonal, except now you also have M in the entry IJ. So M in the ith row and the jth column. And you want to convince yourself, pause if you need to, that really multiplying on the left by this matrix will add M times row J to row I in matrix A. Now this, I'm not going to try to convince you that this is a symmetric matrix, don't worry. But it is triangular. These are all zeros up here. And its transpose is also triangular, just puts the M up here, but then it's all zeros down here. And as we've already seen, the determinant of a triangular matrix is just the product of the diagonal entries. And so this has both Lij and Lij transpose. Both of these have determinant 1. And so, once again, the determinant of adding M times row J to row I, and its transpose are going to have the same determinant. Okay. Now that we've got that under our belts, let's go back to thinking about the determinant of the transpose of a matrix in general. A square matrix. So, okay. If A is invertible, then A can be transformed into the identity by a series of elementary row operations. That's because the identities is the reduced row echelon form of A. And similarly, that means you can get from the identity to the matrix A by a series of elementary row operations. If you swapped 2 rows, swap them back. If you added a multiple, subtract that multiple. If you divided by a scalar, multiply by the scalar. And so this means we can write the matrix A as, well, start with the identity matrix, and then multiply it times one of these elementary row operation matrices, And keep going, and maybe you have to do something like k times in order to finally get to A. But you can write A in this way as a series of matrix multiplications of elementary row operation matrices times the identity. So each of these is the matrix of a row operation. Now, all right, let's take some determinants. Well, the determinant of A is going to be the determinant of this right-hand side. And since the determinant of a product is the product of the determinants, it means we're taking the determinant of all of these guys times the determinant of the identity, which, okay, is just determinant of the identity is 1. And so we are left with the determinant of A is equal to the determinant of all the row swaps. And, sorry, not just row swaps, row operations. All right, now what about the determinant of A transpose? Well, that's got to be the determinant of this product transposed. And then we'll use that property that to take the transpose means you flip the order of the product. The transpose of a product means you swap the order of the matrices in the product, and then transpose each of the matrices. Okay, now again, break that up. We've got the determinants of all of these matrices multiplied together. The determinant of the identity matrix, its transpose is the identity, so that's just 1. And then, as we just saw, each of these elementary matrices, the determinant of the matrix is equal to the determinant of its transpose. So this is just the determinant, the product of the determinant of all those elementary matrices, which is exactly what we have up here. So indeed, the determinant of A and the determinant of A transpose are equal. Yeah, like that. Oh, I said it again. Okay. I think I'm ready to talk about the determinant of a linear transformation. I hope you are too. Okay. So first, suppose we have some linear transformation to Rn from Rn to Rn. Then by definition, by your book's definition, not my preferred definition, but by your book's definition, it has a matrix representation. We'll call that matrix A. And now, in this case, if you're going to define the determinant of a linear transformation to be anything, you better define it to be the determinant of the matrix A, or else no one will like you. But what about if T is a linear transformation just from some abstract vector space to some abstract vector space, not just Rn to Rn where we have an obvious matrix? Can we just pick a basis for this abstract vector space, find that matrix B, the B matrix relative to the basis, and then define the determinant to be of the linear transform to be the determinant of this matrix B that we got? Yeah, we sure can. That's what this says. This is how we're going to define it. So suppose you got a linear transformation from some abstract vector space to some abstract vector space where, okay, it's finite dimensional. Then, all right, this pretentious B is if this is a basis of your abstract vector space. And then B is the pretentious B matrix of the transformation. Then we're going to just define the determinant of the linear transformation to be the determinant of the matrix B that you get. And you might be worried, or maybe I said you should be worried, that there's never just one basis you can choose. Like the basis for a space isn't unique. There's plenty of bases you could choose from. Did it matter which basis we chose? No. Turns out the determinant totally independent of the basis that you choose, which is nice. And maybe we should say something about why that's true. So, yeah, picking a different basis will in fact give us the same determinant. And that's due to this theorem 4.3.5, which I will summarize here. This theorem says that if you have an abstract vector space with two different bases, pretentious U and pretentious B, and then we let A be the matrix of, the matrix of version of that you get from the pretentious U basis, and B is the matrix you get from the pretentious B basis, then in that case, A and B are similar. So that was just a long-winded way of saying that if you have two different bases, the matrix representations under those bases are similar. And then as we just saw, similar matrices have the same determinant. So it didn't actually matter which determinant we chose. So okay, in one sense, this is nothing too crazy. You have a linear transformation, you want to define the determinant for it, go ahead. Find its matrix, find a matrix representation of it, and take the determinant of that. And let's see an example. So let's find the determinant of the linear transformation from the space of degree 2 polynomials to the space of degree 2 polynomials that is given by this. Put in one of those polynomials. The output is 2 times the polynomial plus 3 times the derivative. All right. So first, we have to pick a basis. I always like this one, just 1x and x squared. And now you have to find the transformation of the basis vectors. This is in order to find the matrix B. So the first basis vector, input 1, you end up with 2. Next basis vector, input x, you end up with 2x plus 3. And then your last basis vector, you input x squared, and your output is 2x squared plus 6. And now we use this to create the matrix B. So our first column is going to be, well, all right, this is 2 times the first basis vector plus 0 times the second and 0 times the third. So our first column is 2, 0, 0. This is going to be 3 times the first basis vector, 2 times the second, 0 times the third. So we get 3, 2, 0. And then finally, we have no constant term, 6 times the second basis vector, 2 times the third. So this is our matrix. And then the last step is to rejoice in your good fortune that B happened to be diagonal. Oop, not diagonal. Triangular this time. And calculate the determinant by just taking the product of the diagonals. And that would get 8. So there you go. Not too bad. And I think that's it for today. See you in class.